The outline of the talk, I will start with some introduction, and I will present to you the general idea of what these gambling demons are.
Ya
Then
se
I
me
will
entiende, ¿cierto?
go through the methods that we use to describe this kind of system, which is essentially market theory for stochastic thermodynamics. And then I will present both the theoretical results
Estoy
and
justamente.
the experiment that was done. Okay, so let me start by just going back on the way to original of the experiments of Marx the Demon in 1867. So
Listo.
that time it was developed already the kinetic theory of phases.
Apenas.
The idea that Maxwell imagined two chambers filled by a gas with some wall, separated instead, and in the wall there is some hole with some small trapdoor that an external agent or the demon can manipulate at will. So the idea is that he can see the velocity from the position of all the particles inside the two chambers, so that when there is some particle in this box, which has very low velocity, it just open the door and let it pass to the other one, or when he sees some particle which is very fast in the right chamber, he do the same and just let it pass to the right. So that by doing this, at the end of the day, you will increase the temperature of this chamber and decrease the temperature of the other chamber. And that will be like a paradoxical heat hammer going in the opposite way that the spontaneous flow. The idea is that opening and closing the bubble, the principle will not perform any work. The energy will be in principle conservative. So you will have like a violation of the second law of thermodynamics. So these ideas were also took by Seagal in 1990, did his PhD thesis on Maxwell Demon, and captured quite well the idea of how information is managed in Maxwell Demon. And what he did is to propose what was the first theoretical model for an information engine. This thought experiment consists essentially in having a single particle gas inside the box, which is normalized in the environment, and perform this cycle that you can see there, in which he just first introduces some partition in the middle of the chamber, then look inside to see if the particle is either in the left or in the right. In this case, for example, it's in the right. So then the demon can put some weight attached to the wall and perform some isothermal expansion to the opposite side of the chamber, and just obtain some small amount of work in this expansion. It will be, which is really good. It will be like KT log 2 of work. So, of course, already Silars was thinking about how may this be possible, no? And his conclusion was that, of course, there will be some thermodynamic cost in this part of the measurement. And these were like ideas that were around for a long time. But an exorcism of this Maxwell-Demon paradox had to wait to the development of the information theory. And in particular, it was proposed by Charles Bennett that those violations are only apparent violations if one takes into account the informational cost of the measurement and of the processing of information. So the idea is that if one uses Landauer's principle, Landauer's principle, developed in 1961, one can see that erasing a bit of information has a minimum cost of KT2. So that will like compensate the work that you extract in a single cycle of the cycle. So nowadays, these ideas have led to a more consistent theory of thermodynamics of feedback control, in which you can rewrite the second law of inequalities by introducing an information term, in which stands for the information that is acquired and used in the feedback protocol that you implement. No? And I will just to recall what John Bechofer and Carlos Alvarez talked this morning about this. So there has been also many experiments that try to test this concept, apart from the ones that John told us this morning. There have been other platforms, like for example, in electronic devices, or even in the quantum case, there have been tests to these ideas with nuclear spins, or also in circuitry setups. So, okay, so what we have seen essentially is that the Maxwell demon has two ingredients. One ingredient is to gather information about the dynamics of a system, and the second is to use some feedback using that information that allows you to extract work in a way that will be otherwise impossible. So the proposal that we made is trying to somehow lower the capabilities of the smart school demon. So we allow it to gather information about microscopic dynamics, so that's okay. But instead of having feedback control, we try to reduce this to the minimal expression. We will be just allow the demon to stop or not stop the dynamics at a certain time. So, and this is, we call it gambling demon because it's somehow similar to players in the casino because they are like, or even agents in the market that they can decide to play or not to play again, but they cannot change the rules of the game, so they cannot apply this feedback that change the dynamics of the system. So, so this is more or less the idea that we developed. So we can try to put it like in a game. So imagine that we have this demon, which is an agent that have some work to invest to put the system out of equilibrium, so that he can do that and go up to a final time top. And the game is whether the demon is able to get more work than the changing free energy or not. So that if you do it one realization, you may get more work than the changing free energy, but of course, if you do it a lot of times, in the average, the second law wants you to have always more work invested in the changing free energy. The question is, what happens if instead of waiting for doing this protocol up to a final time, you do like realizations in which you have like different times for every realization, no? Which is what we call a stochastic time. That is, if the demon is able to have some profit by just stopping at a certain smart time of the evolution. So in that case, the idea would be whether it is possible to have work which is less than the change in free energy at this stopping time. So there's an averages over trajectories that may have different lengths, okay, contrary to the first case. Okay, so all what I am going to tell you can be framed in the framework of stochastic thermodynamics, where we have essentially a system which is described by one or several degrees of freedom. Here I just take 1 degree of freedom x, which can be either continuous or discrete. And so because of the noise from the environment, it is a stochastic variable that follows like a stochastic path on time, no? Like for example, this one here. So one of the main achievements of stochastic thermodynamics was to develop a set of relations that called fluctuation relations that were able to extend the second law of thermodynamics to the case of fluctuations and that refine our understanding of irreversibility. So this can be illustrated, for example, that this quantity is called stochastic entropy production, which can be defined for single trajectories of the system, and essentially can be seen to be just the log ratio probabilities of having this path in the forward direction compared to the probability to see this path in the time reverse direction. So, of course, if you think in macroscopic irreversible processes, like for example a glass which is broken into pieces, the observing the time reverse trajectory is almost impossible. But if you go to the micro scale where the fluctuations become important, so for example, you may imagine a onion particle in a staircase potential, you will most of the time see the particle going down, which corresponds to positive entropy production, but sometimes you will see also some instances in which a particle go upstairs that will correspond to negative entropy production. So this negative entropy production is possible in the micro scale, but of course the point is how probability. The fluctuation conditions like this one put several constraints on what are the statistics of these violations of the second law of the microscope. So the new ingredient that so this is well known, the new ingredient that we use in this, sorry, I can change this slide. So the new ingredient that we introduce in this work is the use of martingale theory for stochastic thermodynamics. No? So what is martingale theory? Martingale processes are just a class of stochastic processes that were introduced in probability theory by Paul Levy in 1934, and they just are defined by this property here. Okay, those are stochastic processes and that verify histography. So what this means essentially is that if I have observations of a stochastic process n up to some time t, and I want to infer what is going to be
will be always the last observation that I have. In a sense, this is like processes that are unbiased. No, the best observation, the best guess is always just the last thing that I observe, right? And these kind of processes are used and are well known in mathematics of finance. They are used to model what they call equilibrated markets, which means markets in which you cannot take profit from fluctuations. So because so imagine that M could be the price of some stock, and then if you want to buy it and sell it afterwards, you will see that since the average will be just the price you you have to buy it, you cannot get profit on average. So martingale has very many interesting properties, and in particular, uh, there are these two that were developed by Dupes. So this Dupes optional stopping theorem that relates the statistics of martingale processes at the stochastic times, at the stopping times, with respect to the statistics at the initial time of a process, as well as those maximal inequality. So the point is that it has been shown that in non-equilibrium stationary processes, entropy production it's an exponential martingale, so it verifies this property here. And this is stronger than the standard fluctuation theorem. Indeed, if you take here t equal to 0, you will recover the fluctuation theorem, but of course this is a much stronger statement, right? Indeed, this has been used in previous papers in order to obtain some stopping time fluctuation relations and some second law at the stopping times, as well as some bounds on the statistics of the minimum of entropy production in intervals and so on. Okay, thank you very much. So indeed, there is a recent review that I would like to point out here if you are interested in these things or applications of martingales in physics. But however, all this is for non-equilibrium stationary processes, and the process that I told you before for describing this the gambling demon is non-stationary, so it's a driving process. So what we had to do is so we use this kind of theory, but we had to extend it to the case of driving systems. So the idea is that in the case of driving systems, the exponential of the minus entropy production is no longer a martingale, so this is not verified anymore, but you can obtain a similar martingale process by just adding some extra term in the exponentials. And what is this extra term is something that we call stochastic asymmetry, which is essentially the log ratio of probabilities in forward and time reverse process. So for example, if you imagine an initial distribution for your system and you implementing your driving, you will go out of this distribution up to some final time tau in which you will reach a new one. And you compare this with the time reverse process in which you start here and go back with the time reverse protocol. You will see that this distribution and this one will not be the same in general, right? Because there is irreversibility in the environment, etc. So this is essentially the meaning of this term. So it is an stochastic term, but the idea is that when you put it inside these exponentials, you recover a fluctuation theorem at the stochastic stopping times, and then you have this also second law at the stopping times. So what is important here is that since we obtain here this new term, now this is no longer just greater or equal than 0, but is greater or equal than something that that can be negative. So because this delta can be positive, all this can be negative. So in principle, you can go below zero. So you are not constrained anymore to be positive. So this is essentially that were our theoretical results, and then we wanted to see if this can be applied to some experiment and see how this relation look like. So the idea was to employ a strategy that allows this work extraction, but of course there is the question of how to develop optimal strategies, no, for this kind of gambling protocols. So we still don't know how to optimize that. Okay, so let me just finally thank my collaborators. That was a work that was developed when I was in Trieste. So I was working there with Edgar Roldan and Rosario Fazio, and we collaborated with a group of UCA Pecola at the University of Helsinki, with Diego Subero and Olivier Maillet. So thank you very much for your attention. There is any question for Professor Gonzalez?
Thank you, Professor, for your talk. When you introduce the delta factors, I get a little bit loose with that. May you extend this discussion, please?
Is delta?
The delta factor that depend of the probabilities. Yeah.
This one? Yeah.
Yeah.
Yeah. So this
what is the reason to introduce this delta factor? Okay.
Yeah, we introduced it essentially because it was ULAC in order to verify this relation. But the physical meaning is this one, no? It's the difference in probabilities at for a trajectory evaluated at some time t, compared to the same quantity in the time reversal process. In the time reversal process, you will have another distribution. Instead of this rho, you will have this rho tilde. And the difference between these two, so this log of this log, the probability ratio, is what gives us this term. No? And essentially, if you average over fixed times this, you recover a Kullback-Leibler divergence between these two distributions. But in our expressions, this term appears evaluated at the stochastic times. So in principle, this is evaluated at the different times you stop every trajectory. In that case, you no longer recover this Kullback-Leibler divergence. But in that case, this can be indeed either positive or negative. So you need to ensure that your strategy, your stopping strategy, generates some positive average delta at the stopping times. But if this quantity is evaluated at fixed times, you will recover just the Kullback-Leibler. So it's a measure of the distance between the distribution of your system in the forward and in the time reverse process. So of course, at the time tau, these two will be the same because you are starting the time reverse process as the final state of the forward. But in the middle of the protocol in general, they will not be the same, except if you have some symmetric thing with respect to time reversal. No, for example, something flat, or there will not, you will have the same distribution here and here, or something that if you do the time reverse looks like the forward one. No? Like, for example, if it is something periodic, and if you flip it back, depending on how is the phase, you can obtain the same. In that case, these two will be the same, and you will not able to do that. So you need something really asymmetric under time reversal.
Thank you.
Um, okay, sorry. So you might mention this and it went by too fast for me, but did you compare like this strategy with sort of a more conventional feedback strategy of, you know, sort of the kinds I was doing? Like,
no, we did not compare, but point that perhaps.
I mean, certainly in the Pecola group, they did more conventional feedback previously, so they must have done similar.
Yeah, but not in the exact same setup. But nevertheless, what so if one point for the comparison between these two different ways, to implement Maxwell demon, is that when you do the feedback, you get optimal results when you go in a quasi-static manner, when you work very slowly. Here is the other way around. Here, for example, you can see these are our results for the fluctuation theorem. When you go more or less fast, but if you go slow, like here, so here the final time is decreased. So this term delta goes down because, of course, the most slow you go, the most close to equilibrium you are, and the more symmetric under time reversal everything is. So if you go quasi-statically, you will lose this effect. So this is an effect that only happens if you go more or less
Right.
fast.
But that's I mean, how to say, that's an efficiency per cycle. But if you're looking at power, then in the feedback you would be going faster, right?
Uh-huh.
So that would be more the fair comparison, no?
Yes, yes. Well, I don't know. I don't know well, but I don't. We can discuss later, perhaps.
Hi. So I actually have two questions.
Okay.
So regarding the last one that you just answered, so and the two are related. So so let's make the first one I had before. When you talk about monitoring the system,
Mhm.
You're really monitoring the system you want to look at. So
Exactly.
it's directly measuring something in the system.
Yes,
How?
okay. So what this measure is whether there is 0 or 1 excess electrons in this box, no, in this copper island here. The way to do that is to use this electrometer. That what makes is to put a very with electric current with a very high bias, coupled with a Coulomb interaction with the island, so that when there is one electron in the island, the current gets shifted.
Okay, so you're actually measuring the environment, yeah, not directly. I mean, of course, you get the information there, but you don't change the state of the system.
You don't change it, yeah, because it's this Coulomb interaction that in principle does not change
Mhm.
the electrons. So the electrons are only exchanged with the
Yeah.
leads.
Okay, so a very naive question, which was related to the previous one. Why do you need feedback? It's not enough to measure and then decide to stop or not?
Yeah. This is what we shown, no? That
Mhm.
so the only feedback that you need is to stop but in that case you need this ingredient of this time asymmetry that in principle is not present in the normal setup with feedback control.
So thank you very much for your presentation.
Thank you.
We continue.
Haciendo tu trabajo.
Sí, yo ya tengo síntesis.
And Gabriela, I think they are doing periodically this huge effort to make this event, and always very nice. I think we get the chance to update here in Colombia a lot of stuff with this period. Okay, so I'm going to talk about this. This is actually closely related, some ideas of what we just heard. But so when they ask me about showing my recent work, so my students are going to participate and they are going to show stuff. So I'm going to show some ideas that I have for a new stuff. And so they are very preliminary, the results. The idea are quite clear right now. So we will be talking about continuous monitoring exactly. And so the idea here is I changed this yesterday evening because I realized that maybe in the audience this could help a little bit if I do this slower. So imagine you want to, I want to put together the two ideas, something that we have been working together about a lot about monitoring environments and something about, of course, quantum thermodynamics. So imagine you have your system and you want to know something about this system, but your system is never alone. I'm talking about quantum systems here. So you always have an environment around, and your system is exchanging stuff with the environment. So most of the time, what the system exchanges is information. Okay, and here I'm going to talk about a case in which actually the system is only giving information to the environment, and very seldom is information coming back. So it's what we usually call Markov interactions between them. So when you have this, the kind of description that you have for the system is given by this deterministic master equation. So you have one part here that gives you the unitary evolution of the system, and then you have the jump part, or which actually comprises all the effects that the environment together, I mean, on average, gives over the system. So at the end of the day, you're only working with the system again, and all the information of the environment, you have it here. But the reason for this is that, of course, you're losing information from the system, so you no longer have a unitary dynamics, but you have something else. Okay, so you can ask, okay, what if I try to recover information from the environment? So what if I put around the environment a detector, and I start to measure the environment? Yeah, much like Professor Manzano showed us before. So now I'm not measuring directly the environment. I'm measuring the environment. Yeah. So not the system, but the environment. But let's say I do the measurement. I have my detectors, but I decide not to look what I measure. Yeah. So I just throw away the information. So I ignore this information. So again, if I want to describe the state of the system, I have not gained any information, even though I have measured. I don't know what the results are, so I still have the same kind of description. And the point here is that this remains deterministic. But what if instead of doing that, I sit there and I start to collect all the data that I have there on real time? Yeah, I make a record of what I'm getting there. So in this case, depending on how I do this, I recover certain kind of information, and I can say what is the state of the system. And the state of the system now is going to be conditioned on the outcome of my measurement. So it will depend on what I'm measuring. But its evolution is going to be stochastic. So it's no longer given by a deterministic equation, but it's given by an stochastic equation. So here I'm writing this master equation, which is a stochastic. So here I have, I mean, if you recognize the first part, the deterministic part that I just mentioned before is this one. But now the process of measuring and keeping a record of the measurement adds this other part, which is an stochastic part. This equation is actually, I mean, it's not too complicated in most of the cases. I will show some along the talk. But it's actually also not trivial. Yeah. So this deterministic part has this nonlinear jump part here. And if you see now, I put in my state, I put that it is conditioned. That's why I have this in. So this depends on the record I'm making of the system. And then I have this other part, which gives me now, this is the nonlinear, and this gives me the stochastic part here. Yeah, and I will return to this, and I have given these names because it's going to be relevant later. So I have this deterministic part, and I have this stochastic part. So to complete this, because this is an stochastic equation now, I need to have the statistics of the noises that I have there. Now, these noises come from, I don't know, it's looking weird. But these noises come from the measurement, yeah? This come from the measurement. So in these cases, here we are considering noises that I have average 0, and they have this kind of correlations, but there is an important point. These noises here, like the way I write this equation, they can be complex. And so I can fix certain kind of correlations here with this matrix U. What is behind this is that the way I measure the environment is not unique. I can put the set of apparatus and the way I do my setup, I can change it in principle, and each time I change it, the nature of the trajectories that I get solutions from this equation are going to change. Okay, so what I'm measuring here, what this guy is taking data from, are this kind of currents. And if you see the currents, which is actually what I'm measuring, depends on this U. Yeah? So whenever I measure, I have this. This is the kind of data that I get. I can reconstruct my equations, my trajectories from there. I never do this. I'm a theoretician, so I actually do it the other way around, but this is in principle the way you do it. And this correlation, I have control on it in the lab, in principle. Yeah, I can change the setup, I can change the kind of correlations, and then I can change the kind of measure that I make in the system. And now what I want to convince you in the rest of the talk is that the way I do this matters in terms of what are the results that I get. And in particular, the results that I get in what we have been discussing, in the conference. So just to give you an example, this is a trivial, a simple example to get the idea. We have here a qubit. This is block sphere, and this qubit follows this master equation. Yeah, in case if we are not measuring the system, if we are not monitoring, this is the master equation it follows. So you have here that you have this is a qubit, but you have this forcing, this sigma x term. So this is basically making the qubit rotates around the x axis. But then you also have some damping here. Yeah. And what we have here is just a single trajectory. The red lines are the average over, I don't know, I think 10 trajectories or so. Sorry, and here I have the way I choose to measure this stuff. So I'm actually looking mainly, you see this is the average currents I'm looking at, and what I basically looking is the direction, the direction of the spin, the spin in the direction y. So there's this way of measuring. What it's doing is kind of trying to project the system always in the y-axis. Yeah. So that's why if you look into the trajectory, which is this blue one, it very, very fast brings the spin into the into the YC plane. And there you have just rotations. Yeah, you have these rotations here. And you have, of course, these curves are not continuous. They are stochastics, just like the one you have been discussing here. Now I do the same system, but I choose to do a different kind of measurement. Yeah, and in this kind of measurement, what I'm actually doing is just measuring the noise in the system. I'm choosing here to measure. On average, my signal is 0. So what I'm doing is just measuring the noise, and this will become apparent later and important for the cases I'm going to discuss. But the way now my trajectories behaves are very different. In this case, I'm always forcing very soon the system to go into the YC plane. Yeah, so the X component is really going to 0 very fast. While here, because I'm only measuring the noise, what I have is that the system is jumping from the north hemisphere to the south hemisphere quite erratically. So you have this kind of trajectories here, which it goes to the south hemisphere, then it goes again to the north, then to the south. And here the way it oscillates around the x-axis now changes compared to this one. So actually the quantum trajectories that I get from this setup are statistically different from the ones that I get from this setup. The only thing is that on average, they both give solution to the same master equation. Okay? So now I want to make the connection to heat and work that we were talking here in the conference. So now I'm going to split this equation now in two parts, not in the deterministic but the stochastic part. But I'm going to say, okay, wherever the work is coming to the system is here in the unitary evolution. And this is clear, yeah, because the work is going to come if I have a change in the Hamiltonian, yeah, if I'm driving the Hamiltonian. And whatever interaction that comes from the environment is going, I'm going to call it heat. Okay? And okay, this has been already done. And if you do this, you get this change in your state, which is one part that is work and one part that is heat. Okay, so now I'm going to try to make this connection with, I don't know why it's looking like that, but exactly. So I want to talk about heat and working at just a single trajectory. Yeah, so I mean, the usual experiments that you do here is that you have your system is in certain thermal state. You have your Hamiltonian, which eventually may have a drive. And you have the internal energy of the system, which is the average of the energy of the system. So the way you initialize this stuff is that you make something that we call the two-point measurement scheme, in which you measure the energy of the system initially. So it means it projects from this state to just one energy state. And you do the evolution of the system until a time tau. And then at the end, you do again the measurement of the system, of the energy system. Yeah? And then you compare the change in energy here, and you do the energy analysis in these problems. I'm not going to get into the details because I want to get to the main part of, and I'm running out of time. So again, remember, this was the dynamics. If you just change, you want to see the change in the internal energy, you can put here the change in rho. I did it here. And at the end of the day, you get these two equations. This part here that goes to zero because it's the Hamiltonian with the Hamiltonian here, the trace. And this was the unitary evolution. So you get this part in which you clearly see that this is work. I mean, it depends on the changes on the Hamiltonian. And here you get the heat part. Yeah. So at the end of the day, you can write, this is for a single quantum trajectory, the energy in this way. And I was following here the work of Juan Jose Alonso, which was his study here in our group in Bogota, and did his PhD about these problems. And here you see for this system in which you have, again, a qubit, and you start with the qubit in the Hamiltonian being sigma c, and you make some driving in which you go from sigma c to sigma x, basically following a sigmon. So very, very slowly goes, but at the end you ended up in sigma c x. And you have here some dephasing environments. Well, here you get the signals that I was telling you, the record, and you can see the evolution of the internal energy, which is the green one. And for a single trajectory, it's an stochastic evolution. Yeah? The work does not oscillate that much because it's basically the driving you apply into the system. And then you have the heat that comes from the quantum interaction with the environment. Yeah? So this is not so important for what I want, so I'm going to jump just to gain some time. Now, however, more recently, I mean, it's not yesterday, but it's not that much far ago. The work of Eluard, he was considering, okay, maybe this part of the quantum of the heat, we can split it in two parts. Yeah? One part in which you have the classical part, which has to do with the part of the master equation in which you reproduce the energy exchange with the environment, which is quite classical, and you call it this the classical heat. And then you get the quantum heat that comes from the interaction of the way you measure the environment. Yeah, so this is really the quantum part in which the way you measure in the environment is giving you this feedback into the system. Yeah, and they call it this part the quantum heat. So now, what you get there is you can now divide the change in energy, like in a part which is the work part, the quantum, the heat classical part, and the heat quantum part. Yeah. So now comes the idea we have been exploring is to do this and trying to see if we can manipulate the quantum part to make it zero or to make it use it to our advantage. Yeah. So this is my last transparency. So I'm just going to give you an example of some of the first results that we got. So consider this system in which we have, again, a qubit, okay? And we have a dephasing environment here. So the system is really only losing coherence all the time. Yeah, I'm not going to even have energy exchange with the environment, just losing the coherence. And the way you can see in a single trajectory, and this is the stochastic part, the way I'm measuring. And I have the freedom to choose the correlations here of the noise. So when you do all what I proposed before, well, you're going to get that since I don't have any driving, the system has no work. I mean, it's not work done or it loses energy by work. Because I'm only doing the phasing, so you don't have the classical heat either. Yeah? But on a single trajectory, it seems like you're going to lose coherence on the system. And this is the part of the of the quantum noise, which looks like this after you do the calculation, which is actually pretty simple in that case. But you see, this part depends on the real part of the noise only. So if I can look for correlations on the system, and I know how to do this, if I can do correlations on the system in such a way that I always have imaginary noise in this case, I can also make the quantum noise disappear along this single trajectory. And in this particular case, what it means is that my qubit along this trajectory will not decohere. Because the only effect here that I have from the environment is it comes from the quantum part, which is providing the coherence. Yeah, these classical parts, so to say, are given 0 by construction. Okay, and here I don't even need to put feedback to restore coherence in the system. It's just by the way I'm measuring. In this particular case, the imaginary noise here is precisely when I get the 0 average. So I mean I only measure the noise. I can prevent this qubit from decoherence. And so this is the idea in which, I mean, the way I measure it, it matters for this kind of problems. And so, because it's just a preliminary idea, my conclusion is, okay, I think we got a couple of ideas that shows that if I monitor properly the environment, I can really manipulate the quantum heat in the system. Thank you very much. So this is breakdown this topic.
So there has been like some discussion in the field whether this term should be called heat or not. And, for example, well, I would like to ask you if you think that this should be called heat, or you can say why.
Okay, so thank you very much for the question. I mean, I actually decided to show this preliminary stuff because this is an idea we worked with an undergraduate student a couple of years ago, and we got to some point. And then when I looked the kind of tutorials that we're going to give here in the week, I said, okay, I have a couple of questions in this regard, so this is the place to get an update. And I'm still hesitating to call it quantum heat because in this particular case there is no heat whatsoever in this system that I'm showing here because there is not exchange with with energy. I mean energy exchange with the environment. Yet the term is still there, and you can manipulate it. Yeah, but this is precisely the kind of things that I had in mind to discuss. Mm-hmm.
Okay, perhaps we can discuss later. So I am more prone to call this like measurement work. Like, so in any case,
Okay.
the average is 0, right? But,
Yeah.
But yeah, so we have some arguments to say that this is more similar to work than to heat. Not, of course, the mechanical work that you will do with the driving, but perhaps the work that you do when you measure the system.
Exactly. So the feedback that the measurement provides.
Yeah, like a back action. Yeah,
Yeah,
of the measurement.
yeah, that will be the best word for it. Yeah, back action.
And the other point that I wanted to mention is that so here you use like diffusive trajectories, right?
Yeah, that's what I did.
But when you use like the quantum jump approach, so you have a decoherent process. I think you always maintain a pure state, no, during the dynamics.
So actually here, if you start with a pure state, you keep the purity of the system. So I like to work with master equations, but actually the purity of the system is always fixed by this equation. So if you start with a pure state, it remains pure the whole evolution. So similar to the quantum trajectories, to the jumps. We actually work on this a lot in the group. So we have, for this work, we have the two versions. I just choose the diffusive one because it's easier to follow.
Thank you.
Thank you. Gracias. Mhm. So, go kill them.
Sí, no te falta compartir la
We're going to speak about the quantum work in the in chemistry. So first, I'm just organizers for me to show my work here. So this is our work
I've been doing with Professor Carlos for during my master degree. So I'm very excited to show it to you. Um, so we are going to be talking about some concepts that we've been working on along the week. So the idea here is that we're going to move on from the two-point measurement scheme to other types of work measurements that we may do on quantum systems in order to avoid the initial projective measurement that diagonalize the initial state of the system. Because I'm interested into how coherence effects work in that kind of system. So here first I want to give you like a roadmap of what we're going to be doing. So uh, I'm borrowing the schematic that Professor Manzano showed in his lectures for the two-point measurement scheme, that's TPM. So here what we do is that we measure work as the difference between two projective energy measurements, one at the beginning of the evolution at time t equal to 0. We let the system evolve unitarily. In this case, we're going to be working only on unitary dynamics for the time being because I'm interested exclusively on work for the time being. And then at the end of the protocol, you measure the energy again, and the difference between those two energies gives you work basically. So what we done from here, what we do from here is that we apply a path integral approach, what that was developed by Ken Funo and Kwan in 2019, if I'm not mistaken, where they managed to write the characteristic function of work as a path integral that I'm going to show in a moment. So this is very nice because when you do Taylor expansion on the characteristics um, on the on the time that appears on the Fourier transform in the characteristic function on the conjugated time, you can have you get that the first term of the expansion is the classical work that you get in classical stochastic thermodynamics. So this for TPM. In TPM, we always get diagonal. The initial state of the system is always diagonalized. So we want to avoid that, and that's what the Margenau-Hill scheme is about. So what we're going to do is that we are going to avoid the first projective energy measurement by estimating the initial Hamiltonian by means only of a projective energy measurement at the end of the protocol. So that way we can keep the coherences in the initial state. So this is like the idea. So I'm going to show very fast how the classical limit will look like. So we start from very standard Brownian motion. So this is a stochastic process that depends. This term depends on the potential that you're applying on the system that will be controlled by a parameter that depends on time. This is a damping that depends on the velocity of the Brownian particle, and this is a noise that is basically a Wiener process with zero mean and with pointwise correlations in time. So this is Markovian evolution. So when you look into the energetics of these kind of systems, you have that the energy is simply the kinetic energy plus the potential energy, and when you compute a differential change of the internal energy of the system in the stochastic, for a single stochastic trajectory, you get two terms. So one of them depends on the noise and on the damping that depends on this damping coefficient, the mass of the Brownian particle, and its momentum.
and you get another term that depends on the change of the potential with respect to the control parameter that you have. So the first one we call heat. So this is a differential change on heat, and the second one we call work. So we're going to be interested on the second. So if you compute an integration over time on work for single trajectories, you get this kind of expression, which is a power kind of expression for work. And this is going to be our classical limit for the quantum work. So we will like work in the quantum regime to reduce to this in the classical limit. I recommend very much this book by Ken Sekimoto for studying this, where he develops the whole stochastic approach in the Ito and in the Stratonovich descriptions. So as an schematic, we have here used the universe, that this is our Brownian particle that is coupled to a bunch of harmonic oscillators, that is the BAT, and we couple that to a working environment that is going to be an external system that does work on it. So changes in energy that are on the Brownian particle that are due to the interaction with the work reservoir are called work, and any other energy change that depends on the interaction with the BAT we call heat. Okay, so now the 2-point measurement scheme. So this is already quantum systems. So we're going to consider a quantum system that is described by this Hamiltonian here, depending on this time control parameter, the Hamiltonian of a BAT and an interaction Hamiltonian as usual. So the system is simply the same. We have a kinetic term and a potential term. And now we're going to compute work for single trajectories using the 2-point measurement scheme, as Professor Manzano showed in his talk on Tuesday. So what we do is that we start with an arbitrary initial state in this case. So this one is not necessarily a thermal state. This is an arbitrary state that may have coherences, so terms outside of the diagonal. And at time t equal to 0, we apply projective measurement of energy with result, and we get the result n with the Hamiltonian at time evaluated at time t equal to 0. We let the system evolve unitarily for a time tau, and then we measure the energy again projectively, and we compute work for that single trajectory as the difference between those two energies. So the probability to compute to get initially the result n for the energy, this energy here, is given by this trace simply, and the conditional probability to obtain m, given that we obtain n at the beginning, is given by this transition probability. So we can build up from here the probability distribution function for work by summing over all possible values of work that we may have with these energy differences. So this is basically the joint probability distribution using the Bayes theorem. So is the conditional probability times the probability to obtain this result at the beginning. So we know how to compute these probabilities. Okay, so what we do now is that usually is very convenient to work with the characteristic function of work, because whenever you have, because if you manage to compute the characteristic function of work, you can compute any moment of work by means of derivatives of the characteristic function. So it's a very important object. So when you compute the characteristic function of work, which is basically the Fourier transform of the probability distribution function of work for the TPM case, you obtain an expression like this. So here we have a term that depends on the Hamiltonian evaluated at the beginning of the protocol, a term that depends on the Hamiltonian in the Heisenberg picture at the end of the protocol, and here we always get a diagonalized state, a diagonalized version of the initial state of the system. So this D operator, what does is that it kills all elements outside of the diagonal. So analytically, we show that in fact the 2-point measurement protocol eliminates those coherences from the beginning. So We would like to address what's the role of those initial coherences on the system, on the thermodynamical behavior of the system. So we would like to consider a different approach to work that allows for these coherences to survive. Okay, so now what is done is still on the 2-point measurement scheme in the paper by Funo on path integral approach to quantum thermodynamics is that the characteristic function of work is written as a path integral. This first integral here makes out for the trace that we have here on the characteristic function. Meanwhile, these other terms are due to trajectories going forward in time and trajectories going backward in time, as is common with this kind of expansions. Here, the initial state of the system appears represented again as a diagonalized version in terms of the different trajectories that we have. And we get this action here and accompanied by this exponential that has what is called a work functional due to its resemblance. You can see it down here, due to its resemblance with the classical version of work that I showed you at the beginning. So the idea here is that we are getting a new version of work, of the work functional, that is actually a time average over the conjugated time of the characteristic function. If you see the integral inside is like an average when you divide it by nu, and it still depends on the changes of the potential with respect to the control parameter. So if we perform an expansion of this expression on nu, we will obtain something of this nature that I show down here. So the first term of the expansion is exactly the classical work functional that I showed you at the beginning. Meanwhile, other quantum corrections of arbitrary order can be computed by this formula. But in cases when all the quantum corrections go to zero, we get the right classical limit as we would like to have. So, okay. So I'll have to fast forward this part because this is long, but this is basically the idea here is simply to show what a proper definition of work will look like on quantum systems, and we can ask three things out of them. One is that they recover the classical the classical phenomenological feature that average work corresponds to the average change of energy for closed systems. Two is that the work measurement scheme should reduce to the 2-point measurement protocol for incoherent states. So the classical limit for stochastic thermodynamics is recovered. And we will also expect for positivity and convexivity on the probability distribution function of work. So there is a theorem that tells us that these three conditions cannot be fulfilled simultaneously. So we have to renounce to either one of them. In our case, we're going to renounce to the third. So we're going to be working with quasi-probability distribution functions. So now the Marginal-Hill scheme, what we do here is that we want to compute an estimation of the initial Hamiltonian from a single energy measurement at the end of the protocol. This can be done analytically. In this paper, they show how to do this. And the result is that the best estimate is given by this sum over here, with F given by these generalized weak values over here. So we can identify here the conditional probability to measure N given a result of M at the end. So here is switched with respect to the 2-point measurement scheme. And from here, we can compute retrospectively what the initial energy of the system will have looked like only measuring the energy at the end. So this probability distribution function that we get here from the conditional, we can get the joint probability distribution for N and M by identifying the term on the denominator
as the probability to measure the energy M at the end. And we can build up this nice quasi-probability distribution function that, if you see, is very similar to other kind of uh, probability distribution functions, but here we have a combination, a symmetric combination of projectors instead of a single projector. So whenever the initial Hamiltonian and the final Hamiltonian do not commute, this probability distribution function may have negative values. However, the marginal distributions are always correctly recovered, and we can build up also the probability distribution function of work in the same way that we did for the two-point measurement scheme. Okay, so the same that we did for the two-point measurement scheme can be done for this one. So we compute the characteristic function of work, and it's given in terms of this anti-commutator here in between the exponentiated Hamiltonian at the final time and the exponentiated Hamiltonian at the initial time. And this is basically an average with the initial state of the system. And we can compute, and what we did is that we compute, can you move to the next, please? It's not moving now. And we can compute from here a path integral expression for this kind of expression, where we get here two different contributions that can be written in terms of the two-point measurement protocol work functional. And well, this is the result that we get. So from here, we can read that one of the terms is depending on the forward trajectories of the path integral, and the other one is depending on the backward trajectories on the path integral. And also they are evaluated differently on the conjugated time. So some conclusions. So the TPM protocol works as a good benchmark for to connect quantum thermodynamics with classical thermodynamics in the classical limit. The Novo theorem that I didn't have the time to explain to properly gives us a classification criteria for proper definitions of work. So depending on which condition is violated, we can classify different work definitions. I want to point out here that when you look at the path integral formulation for the characteristic function in the Marginal Hill scheme, you get here the full initial state. It's not diagonalized anymore. So here you still have all the coherences of the initial state. So this scheme allows to assess the initial coherences on the system by the cost of introducing negative probabilities in the joint probability distribution function. And we although we didn't obtain a closed form for the work function in this case, we managed to obtain a path integral formulation of the Marginal Hill scheme. And used as an outlook, well, we would like to compute the semi-classical limit of the Marginal Hill scheme. This may have some implications on quantum chaos and on other kind of problems. So we would like to see how this looks on the semi-classical limit. We would like to know whether it's actually possible or not to define a closed form of the work functional for this case. This same can be done for other formulations of work, like the full counting statistics. In this paper, you can see a lot of them, and the characteristic functions are already computed, but they're not, the path integral formulations are not worked out yet. And it will be nice to look into the dynamics of coherence as a resource on particular paths for these kind of integrals, and to explore open quantum systems, which in the original paper by Funo and Kwan, it's done by means of the Feynman-Vernon influence functional. This is in general hard, so it's not an approach that I would like to develop myself. And that's it. Thank you very much.
Thank you for the nice talk. So, using this formulation of the path integral, can you differentiate between effects of incoherence coming from the initial state and coherence that appear because of the driving part? Will you be able
Can we
to
move
see these
back?
effects in a separate way?
I'm not sure whether we can distinguish those two, but you can if let me go to this one here. So either in the characteristic from the characteristic function here, you can separate the initial state in a diagonal part and an out of diagonal part. So starting from there, you can already assess what the effect of out of diagonal elements will be, and this can be quantified. But I'm not sure whether it's possible to distinguish these two effects. I think that entanglement may not allow it, but one will have to see.
Okay, thank you. So the last talk before the in charge of people from the University of Los Angeles is going to speak about the fast thermal utilization protocol first step topic.
Okay, good afternoon to everyone. Thank you very much to the organizer to let me present my research work here. And for the speakers, thank you very much for your amazing courses. Okay, today I'm going to talk about the two-step protocol. Sorry. Okay, today I'm going to talk about the two-step protocol. This is not working. Okay, so the main idea of this research work is the following. We have, in usual thermodynamics, we have a process that is very slow. For example, when you use a quasi-static transformation that connects one initial state to the another, these states, in principle, an infinite amount of time to get from one state to another. Another important example is when you perturb a system, the system is out of equilibrium, you have to wait a time of the order of the relaxation time of the system. So this is a very slow process. So the idea here is try to accelerate the process. Our slow process, we accelerate the process. In this case, a turtle with a rocket. So, okay, this rocket accelerate the process for connecting from the initial state to the final state. That's the idea. So, in more physical terms, we use the manipulation of the environment via a quadratic potential, where the stiffness depends on time. And we modify this stiffness in order to the system reach a final equilibrium situation faster than the natural relaxation time of the system. Okay, to be more precise, we have a Brownian particle in one dimension, and it's described by the position x, and this particle is tramping an harmonic potential, was a stiffness depending on time. This particle can be described by the Langevin equation in the classical stochastic thermodynamics, not like the previous presentations. We have the term here related with the, we have a term here where there is the viscous term, the term associated with the harmonic tramp, and the noise due to the environment, okay? The noise satisfies the common relation, the average is 0 and is delta correlated. Okay, this equation, the previous equation is quite complicated to solve in general for an arbitrary potential. So we use an approximation here, the overdampened approximation. This means that the size of the Brownian particles is greater than the size of the particles that belong to the environment. And this leads us to this equation that is a first order stochastic differential equation, not like the previous one that was a second order stochastic equation. It's important to notice here that we have a characteristic time
that is inverse with the stiffness. So in order to accelerate the equilibration process, we need to increase the stiffness in order to the characteristic time is lower, okay? This equation describes a particular realization of the stochastic process for each realization of the noise. So that's important to mention this part. Okay, after this equation, we can map this equation to the Fokker-Planck equations. This is the associated Fokker-Planck equation, the previous one. In this description, we are not interested in a particular realization of the stochastic process. We are interested in the evolution of the probability distribution of position. So in order to solve this equation, we use our good friend Fourier, and we transfer the Fokker-Planck equation to the Fourier space in the position variable, and we obtain this equation here. And we use this amazing expansion related with the previous talk. Here, chi is the cumulants of the probability distribution of position. Observe that this cumulus depends on time. This equation has an initial condition, and we assume that the system is in an equilibrium state at t equals 0. So using this, we found that the only not trivial equation for the cumulants is the equation for the variance. So right now, we have two alternatives here. One of them is propose a variance that satisfies a convenient set of boundary conditions. And with this proposal, we can find the stiffness. That is the inverse engineering that Professor Bischofer mentioned, where we assume a form for the variance, and we use some boundary condition here, and we insert in the previous equation and found a protocol. Observe that in this part, we force the system to reach the final equilibrium situation in a time TF. So using this recipe, like a chef, we can find a protocol that connecting to equilibrium state that satisfies that the final equilibrium state is reaching a time lower than the relaxation time of the system. Okay, but we use another approach here. We propose a potential here. This is a two-step function, and this function is inserted in the variance equation, and we solve this equation to produce this result here. At the beginning, this starts as a toy model. Of course, this is a very simplified version of a general control protocol, but at the end of the talk, I will show you how interesting is this protocol. Okay, we have this equation here, and we force this equation to reach a final equilibrium situation at a time TF, and we found this transcendental equation here. So this equation is solved for Km. This Km guarantees that the two-step protocol connect to equilibrium state. Okay, here we can see a comparison between the one protocol that we are proposing in a paper and another protocol that is proposed in Martinez et al. Is given by this Nature paper here. And this is our toy model for two-step protocol. It's important to mention here that observe that the initial state is 1/2 and the final state is 1, and the protocol have to increase a lot in order to achieve the final equilibrium situation. Observe here that the average value of these two protocols is too close to the solution given by our transcendental equation. So it's a relation between the average value for general protocols and the solution of the transcendental equation that we have. Okay, in this figure here, we can see in a more precise way that I already mentioned, when the time TF is lower than the relaxation time, the difference between the solution of the transcendental equation and the average of the more general protocols, the deviation is very small. So we can describe more general protocols using the two-step protocols. So instead of use the KM solution, we use the average value. Okay. For this protocol, we compute the work, but let me mention this is the definition of work in stochastic thermodynamics that the previous presentation showed. In our case, this is the equation that we have. Observe that, as already mentioned, the Langevin dynamics is a particular realization of the stochastic process, depending of the noise. So this variable here is an stochastic variable, so the work is an stochastic variable too. So this means that the work have a probability distribution function. So for the first step, we have, this is the work done on the system. For the second step, this is the work done on the system. Of course, it's a piece-width function. And we can compute the probability distribution using this trick here, similar that the Professor Manzano showed and another presentation I showed too. So we compute this work probability distribution using this and this 3-point function. Remember that the two-step protocols is for time lower than 0 is constant. After T0 and TF is another constant, and after that is another constant. So this means that this process is a Hofstad-Hüllenbeck process. And using this, we can compute this 3-point function. So we successful with that. We found this expression for the work probability distribution with this average here and this standard deviation here. Observe that this is a modified second order Bessel function of order 0, and this function is even for W, and this expression here produce an asymmetry in the distribution of work. In this plot, we can see the good agreement between the simulation and the theoretical prediction of this. Okay, of course, the previous expression for the work probability distribution satisfied the Jarzynski equality given here, where delta F is the free energy that connect the initial and final state. And we can imagine the reverse protocol starting at Kf and with a finished value at Ki. So using the probability distribution of work, we can obtain the well-known Crookes relation. So this make I don't know how to say that, but this give a true of our results, especially with the comparison with the simulations. Okay, so the interesting fact here is we can compute this ratio here, and this ratio here satisfies this equation. Observe that the Bessel function cancels out. That the reason is because it's an even function of W. And here we can see the result for more general protocols, not just the two-step protocol. This plot is for 1/30. We can see that for this time, the more general protocols satisfy a similar relation predicted by the two-step protocol. So we think that this is a universal feature, and right now we are working in trying to prove this. Okay, but no all of these are good news. Observe that the previous plot was for a TF very low, but here we have a plot for a 0.7. This means that there is a deviation of more general protocols for the prediction of the two-step protocols. But still, it's important to notice that more general protocols follow a linear relation. So again, we think that there is a kind of universality in this kind of processes. So we are working right now on this aspect. Okay, let me conclude because the coffee break is waiting for us. So First important conclusion is very general, and is very general for me, for this talk and for any other talks. Using control, we can accelerate processes that are very slow. So we can manipulate the environment in order that the thermodynamic system reach a final equilibrium situation faster than the natural relaxation time of the system. Our toy model describes general protocols for time TF, very low comparing with 1. Remember that I chose units with the relaxation time. The time is measured in relaxation time units. So this means that the TF is very low comparing with the relaxation time of the system. We are working for work in this presentation, but we found expression for the heat done on the system and for the produced entropy of the system. And all of them satisfy similar relation that I previously show you. This paper has been submitted to physical review. You can find this on arXiv. This is the reference here. So thank you very much for your attention. Please, any question or comments are welcome.
There is any question for the audience? For Diego?
Thanks for the talk. I just want to know what's your predilected method for the simulations on the Orsi-Nullebeck process? Is that molecular dynamics or what do you use?
We simulate the noise with standard libraries in Python. It's not too complicated. We simulate the noise. We solve the Langevin dynamics described by in the overdamper regime. After that, we compute the value of work for each realization, and we build the statistics of the work distribution.
Okay, thanks.
Okay, this library is open. You can find in the GitHub of Professor Gabriel, in case you want to use it.
Okay.
Okay.
Thank you, Diego. So I probably miss, so the final state that you want to obtain is equilibrium with respect to the initial temperature, or?
Sorry?
So do you want to obtain an equilibrium state at the end?
Yes.
At the initial temperature, or?
Yeah, at the same initial temperature. Yeah. Yeah, we only perturb the system from the initial state with a initial stiffness and a final stiffness, but the temperature is the same. Yeah, but I think that we can modify this in order to, with different temperature at the initial and final state. Yeah.
Okay. So, and the other protocols that you put for comparison are also for obtaining the same final state, or not?
Yeah.
Okay, okay.
Everything is with the same parameters like Ka and Kf. Yeah.
Thank you.
So we think that this toy model, this start as a toy model to learn stuff, but at the end we see that there is a kind of universality with more general protocols. We think that, and we are working on it.
Okay, but of course, I mean, I suppose the Crookes theorem is satisfied nevertheless, no? But you get like some prefactor on the work, what that was depending on the case, no?
Yes,
So
but
should not that be like the initial?
Yeah, maybe I forget to mention that. Thank you. Maybe I forgot to mention that this equation here is not for the reverse protocol. This
Okay.
is for the forward protocol, just taking in account this minus sign. Yeah, it's a little bit different, but the Crookes relation.
Yeah.
Yeah.
Thank you.
Yeah.
Thank you so much. So I now we are going to invite you to the later.
Yes.
puede imaginarse protocolos más complicados implican lo mismo. Es que nada tiene solución analítica, entonces el de nosotros sí la tiene. Cuando hicimos la simulación,
Afternoon. This is the last session of the week. A very interesting and quite active week. So let's try to finish in a high note. So we will have 5 talks in this session. The last 4 are going to be remote talks, but we will start with Professor Juan Manuel Pedraza from Los Andes University. Thank you, Juan Manuel. Please go ahead.
Thank you. Just a small warning, this will be a very different talk because I don't work on statistical mechanics as most of you, but I use statistical mechanics as one of the main tools in the things that I work. And what I work in is systems biology, right? The idea that cells are in a way like electrical circuits, and then you can analyze them or reprogram them as such, but taking into account that being chemical circuits, you have a lot of stochasticity that you have to handle. But the object of this talk is not so much showing you the results where I've used it, but give you a general overview of a few topics where the methods that you here develop are being used in sort of practical matters. Right? So what you probably already know is that enzyme kinetics are representing and modeled using the basic method of statistical mechanics. This is sort of the main thing, and also protein folding is one of the applications that is very well known. So I'm not going to stop there so much today, but more talking about gene expression and the consequences for the way cells work of the stochasticity that is inherent in the type of processes that you look at. I will not go into the sort of quantum mechanics of it. There's a whole other area that works on the quantum mechanics of biological molecules, but I will not touch on that today. So just to give you an idea of the kind of things where you might not expect that statistical mechanics are useful, this is a result for people studying the evolutionary process as a stochastic process, but it has been modeled as a stochastic process for a long time, but it had been done so in a very non-formal way, just saying, oh, well, it's stochastic, so you can't just say this is going to happen. You have to do many copies of an experiment. But now people are starting to use relatively advanced methods of statistical mechanics and are beginning to get descriptions of the evolutionary processes on simplified, idealized fitness landscapes, but that allow them to design ways of controlling evolution. For example, when you're all familiar with modern cows, which produce crazy amounts of milk. Those are not the natural cows. Those have been selected artificially for many years. Well, that process can be optimized just in the way we saw that you can do external shocks that can make a system thermalize. You can do selection that is guided by detailed models of the stochastic process of evolution to draw the system towards the optimum that you want. Again, this is just to tell you a little bit of it. I'm not going to stop on this too much. Another interesting application is looking at the sort of diffusion process within cells in detail. For example, there's something that you probably hadn't asked yourself, which is how the machinery that reads the genes finds those things. Because for a gene to be read, to be expressed, a polymerase, a big molecule, has to go around doing random diffusion and find a specific bit of DNA. But this has to happen over and over again for a gene to work the way it should, because you need thousands of proteins, right? But the problem is, if you think about it in 3 dimensions, the probability that you arrive at the same place again tends to 0, right? So how does it work? How do you find something in 3 dimensions? And some very interesting studies have shown that what happens is it doesn't do the search in 3 dimensions. It goes in 3 dimensions until it finds the DNA, and then it does a search in 1 dimension until it finds the site that it's looking for. And if it wasn't for that, it would never find the gene that it needs to express. So again, this is not what I'm going to stop in, but to show you different applications. The 2 things that I'm going to stop a little bit on are these. One is phenotypic variation, fitness, and information. So the idea here is that gene expression, as I said, is very stochastic. So a cell produces a protein, but the number of proteins is fluctuating all the time, and we can measure this. And that means that when you're talking about what a cell does, what a gene does, it's not it produces 3,000 proteins, but it has a distribution of proteins that can be interpreted as a population of cells will have each cell doing something different, or a single cell will be fluctuating over time, right? And this is measurable experimentally. So this is just one simple setup that we did to measure this, where you have one gene controlling another gene, and we can control the first gene externally. And what we see is the way biology is usually done is you look at the averages, and you see that as you induce with an external chemical, the first gene turns on, then the second gene turns off. But if you look cell by cell, what you see is that, for example, this point, when this gene is starting to turn on and this one is starting to turn off, if you look at the individual cells, what you see is something like this, that this is what the first gene is doing, this is what the second gene is doing, this is what the average is doing. So if you assume that all the cells are doing what the average is doing, you will be awfully wrong. The cells are doing completely different things. But this is very structured, right? It's not just a Gaussian cloud. It has very non-trivial correlations, and you can infer things about how genes are connected from this type of measurement. So it's very useful. And these fluctuations are important in two ways. If you're trying to make a multicellular organism, you need to control them, because otherwise your cells might get confused and your liver cell might think it's a neuron and things get very messy. But also it can produce phenotypic variability that is useful. If you have a population of bacteria, for example, those bacteria will be doing different things. Each of them will be expressing different things. And this can be a strategy. So what we know now is that phenotypic variability is a strategy that evolution has developed. So one way to think about it is this. If you imagine that you have a cell that has different possible states, say the different colors, and an environment that has different possible states, what you could think that the cell is doing is that it's in one particular state and it's growing, and when the environment changes, then it slowly changes to the other state and starts growing again. If the environment changes again, then it will change again. But another possible strategy is that you don't even measure the environment, you just randomly change. And then what happens is, if you happen to be in the right state, then you will grow, but you will keep changing into the wrong state, and then you will stop growing until the environment changes, and one of the ones that was right by chance beforehand will start growing. And then when the environment changes again, then the ones that happen to be wrong into the right next state, then they will grow. What nature actually does is a mixture between those things. So you might think that this is a better strategy, but if you think that measuring has a cost, it has a metabolic cost, that if the environment changes very rapidly, you might never get to the right state because you take some time to change. The being wrong, even for a moment, might be deadly. If, for example, the new environment is the presence of an antibiotic, if you use this strategy, you're dead. But this strategy is also not particularly effective. So what the cell does is something intermediate. They measure partially, and then they change with probabilities that depend on what they've measured. So it's something intermediate. They do measure, but they don't deterministically change. They change probabilistically depending on what they've measured. But that gives questions on how much information does a cell have on the environment. So this is let me explain this a little bit. So this is the only measure that we have of an actual fitness landscape. So this is for one particular system in a bacteria, where it's trying to adapt to different sugar concentrations. And this is what the cell is doing, the gene expression for one particular gene. And what we see is that the cell naturally does this. This is what the response is for a natural cell. But we can modify the cell in such a way that we can decouple the response from the environment and explore for this environment and all these possible responses, for this environment and all these possible responses. And we can explore the full fitness landscape and just measure it. And then we have this. And as you can see, what happens is, if you're a particular environment, the optimum is what the cell naturally does. So the cell is naturally going over the optimum of this fitness landscape. But what happens is, if this curve is for the average. If you look at what a particular cell is doing, as I've shown you before, everything is fluctuating. So what happens is the cell needs to optimize its environment, but it's subject to an imperfect measure of the environment and imperfect control over its own response, right? So let's write it this way. So we want to maximize fitness, but the average fitness will be the integrating over all possible environments. So S is the environment, G is the gene. So over all possible environments, over all possible genes, we have a certain fitness function, the fitness landscape that I show you that we measured, and the probability of having a particular state of the cell in a particular state of the environment. And if we write it like this, we can separate the environment. So what we're saying is, okay, the environment might be fluctuating with some distribution, but this is what the cell is actually doing. So depending on what the environment is doing, the cell is trying to do something. So this is a conditional probability of the cell doing something given an environment. And then we integrate the fitness over that. And then what happens is that this can be interpreted very easily. So this is the environment. This is what the cell is trying to do to what it perceives of the environment. And this is the fitness function that is given by the biochemistry. But then if the cell could know exactly what to do, like I said before, if it knew exactly instantly what to do, then it would just go to the optimum, right? Let's assume there's some function, the gene, that corresponds to the optimal of the fitness function for that environment. But it cannot control precisely what it's doing because, as I said, all genes have inevitable fluctuations, but also the environment is fluctuating and the cell first can't measure it precisely, and it's also not measuring instantaneously, so it has some delay in the measurement. So that's why it has to do a probability. It has to, what the cell does is not saying, for this environment, I will do this, but this is the distribution, the probability distribution of things that I will do given this environment, right? And then graphically, what we're doing is this. So if I had this particular environment and I knew what it was and I could respond perfectly, I would go here. This is what the cell does on average. But if I'm an individual cell, then that means that the average of the fitness function is just the value at that optimum. Given that I can't control perfectly what is going on, I'll have some distribution of gene expression, and I'll try to be at this point, but I won't be able to. So my fitness will be the integral over this bit, the probability of expression given the environment. But since I can't know what the environment is doing exactly and the environment is fluctuating, what I have to do is integrate over the environment, and then for each possible value of the environment over the distribution of expressions that would come from that particular environment. And what happens is that if you do the calculation in terms of what the information that the cell has on the environment, so we're using here standard information theory definitions, what you can prove is that if you want to optimize the fitness, the average fitness, given a particular value of the information, the mutual information between the cell and the environment, you can do either one, like either maximize the fitness given a particular value of the information or minimize the information that you need to attain a certain level of fitness. What you can prove, is that what you get is something that we know from classical statistical mechanics very well. You get something that looks very much like a partition function. And this is, so the interpretation here is completely different. Here, the energy is really the fitness, but the mathematics that we use are exactly what we use from classical thermodynamics. So this is to show you that even without going into all the sort of fancier things that we've been discussing here, you can do things that allow you to sort of say coherent thing about how biology works and how evolution works in very classical statistical thermodynamics terms. The other topic that so the key takeaway here is just fluctuation in gene expression are the basic of phylogenetic variability, and it's unavoidable, but also that information is just as crucial as energy for determining evolution. So when you try to use evolution to predict things, it's very difficult. The only case where we've been able to do that is in cases where you can determine very well the energy of every option, and then you can predict things. Well, here we've, this paper, that's not my work. This is Bill Bialik from Princeton. What they've done is shown that information is also a quantifiable thing that you have to optimize and that you can use for predicting evolutionary processes. And then the other thing that I wanted to tell you a little bit is something that we're doing 3 minutes, okay, in collaboration with the HALT lab at NYU. And it's this. So the question is, how does aging work at the cellular level? So aging works at the organismic level and at the cellular level. We can see single cellular organisms age. And one of the things that we've noticed using a combination of microfluidic systems that we developed and a system that they developed, which is a fluorescent particle that is exactly the same size as the ribosome, so the sort of main molecular particle that determines expression of genes. We've studied diffusion, and we see that diffusion changes with age of the cell, right? But the interesting thing is they were doing some measurements where they were seeing anomalous diffusion, so it's subdiffusive, but that it changed in weird ways as the cell aged. But they were looking only at the diffusion coefficient, right? These are mostly biologists. So David Duran, a doctoral student of mine who's now doing his I visited an internship there, was looking at their measurements. So these are measurements done mostly by Sutping Lake. These are microscopic measurements of yeast growing in a microfluidic trap. And it's kind of hard to see, but young cells have different diffusions of these particles than old cells. As you can see, these are diffusing very slowly. And what we did is look at diffusion, but more at the process itself. So instead of just trying to determine a coefficient of diffusion, we determined what the distribution of steps were. And what that allows us to distinguish is what are the mechanisms that are doing this, because what could be happening is simply that the cell is becoming denser with junk, so that we know that happens as cells age. But also recently it's been determined that organelles are increasing, so there's large things that are getting bigger within the cell. So it could be that it's doing either just diffusing less as its viscosity increased because you have more junk within the cells, but also it could just be have confinement because there are things in the cell that are growing and are reducing the space. So it could be reducing the sort of the effective dimensionality of the diffusion. And what we find, let's do this quickly, is that, for example, if you look at the angles, so the distribution of the angles of the bounces for these particles, we can track these particles at 10 millisecond resolution. And what you see is that it's consistent, the change in the angle is consistent with the things that are being more confined, because it's more likely that you will completely bounce back rather than just have a random angle, which you would have if it was because of the junk that is in the cell. And so looking at this from more of a physics perspective of looking at the process of diffusion in more detail, we can get biological information. So for example, if you look at the alpha, in the T to the alpha way of writing the diffusion, what you see is that it divides into groups. So what it's saying is that certain parts of the cell are having different effects on the mobility of these particles. This is important because the expression of the cells, or the functioning of the cell, depends on these molecules reaching their targets. And what we're seeing is, depending on which part they're in the cell in, they're being, so both effects are happening. They're both being crushed by the organelles that are growing, but also there's more junk along the way that is reducing the diffusion. And this explains very well what they had been seeing and couldn't interpret when they were looking just at the diffusion coefficient. But now, you have an interpretation that gives you more information about what's happening within the cell. So this was just to, let me just, so the main takeaways of this part is that diffusion changes our cell age, and there's something like a glassy transition. It's very similar to starving cells. So an effect that has been observed is that if you starve cells, certain effects look like aging, but actual aging gets slower, and that's one of the things that biologists are trying to determine. But what, as physicists, what we can say is that the interior of the cell, looking at the diffusion characteristics, works more like a glassy transition. So it's not like a liquid where things are just moving in normal Brownian diffusion, but there's a transition where it becomes glassy, more like a gel, and that can affect a lot the working of the cell. So the hypothesis that we're testing right now experimentally is that what happens is that it's more like the grease that you have when you have chicken in the refrigerator, that it becomes solid, and when you take it out, even when you get back to room temperature, it's like a gel, but it's not liquid. So the hypothesis that we have now is that the cell is sort of like that. And what's happening is that the normal metabolic processes of the cell are melting it. So that allows for more normal diffusion. But as the cell ages, metabolism slows down. And that means that, and the cells get larger. We've seen that experimentally. What happens is, what we think now is happening is that the sort of heat that is released by the metabolic processes is not enough to melt the interior of the whole cell. So you only have sort of small bits of the cell that are melted and that work as they should, but the rest of the cell is sort of congealing slowly. And in some sense, that would be where you get completely congealed at the cellular level. Anyway, I will stop there. I want to acknowledge the sort of measurements that were done in the whole lab and the work of David in analyzing those things. And yeah, just let me stop there. Thank you.
So I suppose that some of what keeps a cell fluidized in your language is molecular motors running all over the place. And is there, when you get this glassy transition, if you were looking for activity of motors, would there be a transition in that too?
Yeah, so what happens is those motors get recycled all the time, but the recycling requires expression of the genes that make the proteins that make the motors, right? So if the diffusion slows down, the rate at which you're replacing the motors slows down, so even the active part gets reduced.
So the population of active
The,
motors.
the population motor effectively get reduced, yes.
And does that go through some kind of dramatic transition? Like, I mean, when you say glassy transition, that suggests something, you know, in a relatively short, I guess, aging time would change pretty dramatically.
Yes. So again, this is for yeast cells, right?
Yeah.
We haven't been working in human cells,
Yeah,
but in
yeah.
yeast cells, what you see is that the cells age very slowly, and there's some point where there's a dramatic drop in the diffusion, and the cells are not as motile as human cells, so the effect of active transport is harder to see. But yeah.
But if you were just to like you know break it open at that time and try to count how many motor proteins you could find, you would find less than.
Well,
probably.
yes, less of the ones that are folded correctly. So what happens is while working, they tend to malfunction, and you still keep them. That's part of the junk that I was referring to. But normally they replace. You just make more.
Yeah.
But then if you can look at the ones that are active, and there's ways of doing that, then our prediction is that you would see that there's less and less of the ones that are working, and it's a transition. So it's very clear that you see that things are aging, and then it just goes all downhill very fast. Cool.
Any other question? Comment? No? If that's not the case, let's thank Professor Viernes.
Okay, so, well, the desk here contacts our next speaker. This way. So
cryo-electron microscopy images, and all very statistical mechanics inspired. So I'm going to tell you a little bit about single particle cryo-EM. Then I'm going to talk to you about the method that we've developed in our lab to extract free energy landscapes and probability distributions using the cryo-EM particles. And then I'm going to show you some conclusions and perspectives. So in cryo-electron microscopy, we have copies of the same biomolecule. And these biomolecules are in unknown orientation and unknown pose and in an unknown conformation. And so then we flash freeze them very quickly, and a thin layer of these biomolecules in amorphous ice is imaged using a transmission electron microscope. So because we use a very high energy beam, what happens is that we basically destroy the sample, and our images are very noisy. So the signal to noise ratio is, say, 0.01. And so it's difficult to extract the differences in projection direction and in the conformation of the biomolecule. And so far, cryo-EM has assumed that these proteins, these biomolecules, have the same conformation. And basically the problem has been reduced to just finding all the different projection directions and being able to reconstruct a 3D density map, a 3D structure of the system. And so basically in the last 10, 15 years, cryo-EM has gone through the resolution revolution, in which advances in the detectors and in the algorithms led us basically to about 3 years ago have atomic resolution in our density map, so basically equal X-ray crystallography. And in 2017, the Nobel Prize in Chemistry was awarded to the developers of both the freezing and the analysis techniques. However, recently, the grounds of cryo-EM has been shaken because basically it was only concentrating on solving protein structures. But then we had AlphaFold, Rosetta Fold that came in and started predicting conformations that took 5 years or 6 years the experimentalists to solve. And so basically one of the questions that the cryo-EM community is asking themselves is, what are we going to do now? And so one of the lines can be developing better and cheaper detectors. Another line, which is the one that I'm very interested in, that I'm going to talk to you more about, is extracting a little bit of more conformational variability, extracting free energies. And there's another line, which is in situ cryo-EM, in which you don't have copies of the same biomolecule in solution, but you take a picture of a cell and then try to analyze this. And this is a very challenging experiment. Okay, so the amazing property of cryo-electron microscopy is that we have individual images of the biomolecule. And because the freezing is done very rapidly, it is possible to trap these images in different conformations. So you can imagine basically that cryo-EM is taking pictures of a horse running, and then it scrambles these pictures all around. And so, however, as I mentioned before, analyzing these different conformations is challenging. And so what cryo-EM typically does is it does 3D classification, in which you start sorting out your particles, making 3D reconstructions. But in the end, what is typically done is that you use 15% of your data, the particles that correspond to the most rock solid structure, and everything else is basically thrown into the trash can. And so why do we discard so much data? Is there anything biological that we can learn from all the different conformations that we typically discard? And so we started thinking about the methods to extract free energies from cryo-electron microscopy due to its single molecule nature and potential. And so basically, I don't need to explain to you here. So basically, the probability of configuration of the molecule lives in this very high dimensional space, 3 times the number of atoms. And typically, we work with proteins that have between 10,000 and 100,000 of atoms. And so basically, we have our probability given by the Boltzmann factor. And typically this is too complex. And so what we do is we project down along some collective variables, or sometimes the chemists call them reaction coordinates. And so basically we can have the free energy along this projection. And so something interesting, like from the biological perspective, is that we don't have the protein in one single state. Well, not only the folded state, which is the global free energy minimum, is relevant, but really all the metastable states of the system are important. And it's important to find the difference in the free energy, but also ideally the barriers between these states, the activation barriers. So our general framework is the following. We say solving both conformations and basically pose and conformations is really challenging. And so what we do is we build on methods developed for the molecular dynamics community, the computational simulation, atomic simulation community, in which we use, for example, MD, molecular dynamics, to give us a set of hypotheses, which are our conformations. And so we assume that we have explored sufficiently well the conformational space, and that there is this initial probability given by the MD molecular dynamics Hamiltonian, right? But we know that this is wrong. It's a classical potential. It's invented by humans. And so basically what we want is we want to use the data to refine the ensemble, to do ensemble reweighting, reweight this ensemble, and get an information about the distribution of our conformations, really given the data. And so for this, we're going to use Bayesian analysis. And so what we do is we assume that we have our single particles, our single images of the biomolecule, and that we have a set of conformations from molecular dynamics. And so basically, using Bayes' theorem, we would like to know, ideally learn an approximation of this Hamiltonian, which is given by the product of the likelihood and a prior. And so we assume that each image is identically independent and identically distributed, and these are not average observables. And so basically, this product means that they're IID, and then we have this integral that basically compares each image with each structure. And so this is basically the likelihood of the image generated by a structure. And then we have this term that relates basically to the probability of that structure. And so this is the thing that we're going to optimize. But because we have this integral that is basically over all conformational space, it's intractable. It's basically impossible to study. And so what we do is we're going to propose some methods that basically make this integral tractable. Okay, and so we started by developing a method that just calculates a free energy along one dimension. And so what we assume is that from molecular dynamics or some other technique, we have a set of path, a transition path that takes me, say, from a relevant metastable state of the system, a closed state, to an open state. And then we write basically the probability of an image given by this factor, which is I assume that all my images come only from structures in this path. And so with this, we can basically make our posterior tractable. Basically, we are killing the integral here. And then we can use this framework with individual cryo-EM particles to basically extract, using, for example, Monte Carlo methods, and then expected free energy value along this path, given the cryo-EM images. And so this is an example of using this with real data. So we have two protein conformations, two conformations of the same protein. One conformation is with calcium bound, and the other conformation is with calcium unbound. And there's a database of images where we basically have all particles, not the ones that are filtered out to create the high resolution instruction, but the ones, all the possible particles in that are given by this thermodynamics. And so basically our question is there a population of this other state in the data that has calcium, because we expect there to be some type of equilibrium. We don't expect all particles to be in exactly the same state. And what does our free energy look like? And so basically we use theory molecular dynamics to generate a conformational path between one state and another. And we apply our method, and very nicely we confirm that the global free energy minimum is the calcium bound state. And also very interestingly, we find that the calcium unbound state is a metastable state. So this metastable state here in the system. And so basically this confirms that we have some signal that indicates that we have several metastable states in our system. However, something that our collaborators have been telling us, the experimentalists, they've said, but maybe the initial path that you create from molecular dynamics is not perfect. And so what do you do with this? And so now I just want to tell you about how we extend this into many dimensions. And so this is a work that just came out this year. And so we have, this is basically the big theory that is intractable. And so now we do what we do instead of building a conformational path. What we say is we're going to cluster all of our structures from the molecular dynamics simulations, and we're going to use the representative cluster centers as a proxy of are the points in our conformational space. So now we're not working in 1 or 2 dimensions, but we're really working in the space of the number of atoms of our system. And so basically, this is what we do. These are now our cluster centers. And what we say is, look, our cluster centers, they're going to have a weight. And this is why we call the method ensemble reweighting. And so basically, now we use our theory to extract the weights of each conformation. And so, but basically, we can say, okay, what are the most probable weights given my images and given these sets of cluster centers from my molecular dynamics? And so we tested this on synthetic data. This is like the harmonic oscillator for molecular dynamics now. It's a system that we can run basically forever and have convergence. It has 3 metastable states: a folded state, which is basically a beta hairpin completely formed, a misfolded state where there's a shift in the hydrogen bonding, and an unfolded state. And so we have 2 independent ensembles. We have one ensemble that generated the structure, the cluster centers. And we have another ensemble that was using a different force field that generates the images. So basically, structures that are given in these images are not found here. The exact structure is not found here in the ensemble. And also something interesting is that 2 force fields give very different free energies probability distributions. And so basically here, what I'm showing is this is the free energy of our structure ensemble. Here I'm plotting the root mean square deviation with respect to the misfolded and to the folded state. And this is the free energy for our image, our data ensemble. And you can see that basically that the misfolded structure is completely lost. There's no misfolded structure, and this unfolded state is more elongated. And so what we do is we plug in the images from the ensemble and our cluster centers, and then we do the reweighting. And here is a plot of the reweighted ensemble. Something very nice is that basically, as I was mentioning, we're not fixed on the collective variables that we choose. We can choose a posteriori different collective variables in practice and see how the free energy looks like in those cases. Okay, so this is basically all I had to share with you. And something that we really want to do in the group is lead cryo-EM toward a quantitative characterization of conformational ensembles. And thank you very much for your attention.
So thank you very much for the nice talk. Are there any questions? Yeah.
Hey, thank you for the talk. I had a question. When you showed the conformational space, there's another minimum. Is that when it's bound to a single calcium molecule?
It's when it's bound to 0, no calcium molecule.
Yeah, but the one in the middle. So
good question. Yes, we don't know. That's a great question. So we don't know. So we because basically we're projecting down. We still haven't really. So what you would have to do is you would have to do a hard classification and then collect the cryo images from here and then see what your reconstruction looks like. But we haven't done that yet because we only had like 20,000 particles to calculate the statistics over. But it's a great question.
Yeah, another question is, when you're talking about the conformations, do you incorporate sort of the molecules of waters around it, or do you just work with the individual protein?
Yes. So so unfortunately, we due to basically the high dimensionality of the system, we typically work only with the conformations of the protein. But I think in the future, we would like to work with like the water molecules, but there's several challenges. So the first one is that basically because the images are so noisy, it's difficult to really pinpoint where the waters are. Like when you do X-ray crystallography, your crystal waters are very, very clear because they're in all places. And so I think something like that you could do with cryo-EM. But I don't know if there's a concept of crystal waters in reality when you freeze, right? So yes, so for the moment, only protein conformations.
Okay, thank you.
Thank you for the talk. Very interesting. Well, there's a method that's been used to compute free energies based on the Crookes relation of the work and a forward process.
Yes, yes, yes.
I was wondering if here you can do something like that, or it's very difficult to keep track of the work done.
It's a good question. So here in principle, we're not doing any work in principle, right? So you can imagine this as your instantaneous, or at least our hypothesis is that we instantaneously freeze and we trap them completely in equilibrium. So there's no work. But if you would think, oh, there's some like force-induced motion due to freezing or something like that, maybe you could think about that the work lowers your free energy. But this is, I would say, this is more like, basically, we just have to count with very noisy data. We don't have to put something external on the system to probe the free energy.
Thank you.
Thanks.
So thank you very much, Pilar.
Okay.
Bye.
Thank you.
So our next speaker is Isabela Cristina Hoyos from Universidad del Quindío. Her talk title is Explaining the Complexity of Colombian Climate from the Non-Extensive Extremal Behavior. So, are you there?
Yes, I'm here. Can you hear me?
Yes, we can hear you now. You could share your presentation, please.
Okay. Good afternoon, everyone. I'm Isabel Hoyos, and we are changing a little bit the topic from biomolecules to climate. This work is shared with the Professor Boris Rodriguez from Universidad de Antioquia. So, give me a second. Oops. Okay, let's start with a brief short overview about Colombian climate. So the main feature in Colombian climate is the split of the Andes in three branches. We have a very heterogeneous landform, and we have a very high diversity of life zones and climate zones. And also we have a lot of moisture, source of moisture that becoming rainfall in Colombia. We have moisture coming from Orinoco Basin, Amazon Basin, and also from tropical and subtropical Atlantic, but also from tropical and subtropical Pacific. In this picture, we have the representation of a Pacific Colombian Basin in green here in this in the map, and also we have the Inter-Andean or Caribbean Colombian Basin in yellow, in background, yellow background here. So this is a schematic representation of the complex structure of moisture sources that becoming in precipitation over Colombian terrain. So, and also we have the annual migration of the intertropical convergence zones that is modulated the structure of annual cycle of precipitation and temperature over the terrain. So what we know about the structure of the origin of moisture becoming in precipitation is that near 58% of the moisture is coming from terrestrial areas, so Orinoco, Amazon, and also moisture from local recycling, and 42% of moisture is coming from oceanic areas. This is a very nice word. We use transfer information for determining the other sources of variability in the Colombian climate. For instance, El Nino, or some global phenomena that are happening in very remote areas. So this is a very nice word because you can see how the structure of how the Colombian climate, that is in this black square, is highly connected with.
Isabel, qué pena. ¿Puedes hablar un poco más cerca del micrófono? Es que aquí en la sala no se escucha tan bien.
¿Ahí?
Sí,
¿Aló?
mejor, mucho mejor, gracias. Sí.
Okay, so what we know is that the Colombian terrain is highly connected. The climate in Colombia is highly connected with remote areas. In this picture, we can see that the annual cycle of precipitation from the Interandean region, that is the green color in the map, over this map. So we have a bimodal cycle with two different kind of seasons. The first dry season starts on December to February, and after that we have a wet season from March to May. And after that, we have the second dry season from June to August, and after that, we have the second second wet season, that is from September to November. So we have two very wet seasons in all of this area that is the Interandean region. So this is important because I'm going to show you a couple of extreme events in Medellin, in Bogota. So there are cities located in this region. So maybe some of you remember Bogota, January 18 to 2015. This is a very extreme, very well extreme, because if you remember, this is the first dry season, right? This is January, that is a very dry month. And also we have this kind of extreme in Medellin on October 29 in 2014, but both are very rare extremes. But the first one is more rare than the second one, because this occur during a very dry month. And also we have a kind of very rare extremes. This is in Medellin on December 1st, 2 years ago. And you can see the results of the extreme. And this one is 1 year after, in August 1st, also dry season. You can see the bus, yes, the bridge over the bus. And in this picture, this is very early this year, 2023. Another kind of extreme event in the dry season, right? So how we understand that kind of phenomenon? So climate extremes are defined as complex phenomena that emerge from interaction that occurs on multiple spatio-temporal scales, and they are characterized by long-term memory, high information content, and positive and persistent feedback. All of these conditions drive the system far from equilibrium, so the extremes appear. So this framework for extremes need a new kind of form of entropy. So the non-excessive entropy that was proposed by Salis 23 years ago, we have that the ergodicity is just one of the possibilities of microscopic mixing in complex systems. And this is not necessarily the generalized behavior. So what we want to do in this work is to sit the problem of extremes in the complexity framework. When you have extremes events, you have the emergence of something new that cannot be represented by the arithmetic sum of the different parts. So we need a non-extensive framework for entropy. So this is the entropy, the Salis entropy, that they provide a very nice set of distribution functions that are characterized by the parameter Q. This parameter classify the kind of complexity that is expressed in the system. Q is able to provide a measure of how far is the system from the Boltzmann-Gibbs canonical entropy. We can identify some kind of universality in the data. We also have some information about long-term interaction, and this reveals the multifractal structure of data. So I'm going to show you, I'm going to focus on the two first characteristic, but if you want to see in the paper, we have a lot of discussion about the others prepared. So we use the Q exponential distribution that is not really an exponential distribution. It's more like a kind of power law distribution. In the limit with the Q equals 1, we recover the exponential distribution. And we have the parameter beta that give us information about a scale of the extremes. We also focus on excess over 90% percentile, and this is a dynamic percentile that is used to avoid some kind of clustering of extremes due to seasonality or a very persistent global climate phenomenon. Okay. So summarizing the meaning of the Q parameter, if you have a Q index less than 1, we have bounded distributions. If we have the Q parameter between 1 and 2, we have unbounded distribution. So that means that we don't know exactly the extension of the extremes. We don't know exactly the states that the system will be visit. And if Q is equal to 1, we recover the canonical Boltzmann-Gibbs entropy forms for the distribution, right? And also remember that this is a very nice quantifier for universality. So in this map, we can see the results for temperature, and this is the ordering. So unbounded distribution, the first data, the second one is for bounded distribution, and the last one is for the limit when the Q is equal to 1. So for temperature in the Caribbean catchment, we can see that the main behavior of the behavior of extremes in temperature is mainly unbounded. The same for Pacific catchment, 50 and 50, more or less. And for precipitation, we have a very similar experience. Oh, I'm sorry, this is in the correct in the incorrect order and compare with the first one. Here we have bounded distribution and bounded distribution, and the last one is the same. It's the canonical Boltzmann distribution, and equals in this part. We have bounded, unbounded, and we have the classical Boltzmann distribution. So the main measures in this couple of figures is that we have very predominantly unbounded distribution. That it means that the set of climate extremes are very complex. If you can imagine that a kind of chaotic behavior, that's not exactly the chaotic behavior, but you can think about it like highly complex, a very highly complex structure in data. So if precipitation and temperature behavior of extremes are coming from the same kind of universality, the same kind of processes, you expect that when we draw the Q index for temperature and Q index for precipitation, the points are over the blue line, but what we have here is a very different picture of this kind of extremes. What we have is that the extremes of precipitation, yeah, and temperature are the phenomena underlying the emergence of this kind of extremes are very different, are not in the same kind of universality for the same place, right? And the last picture here. So what we did is to address the question how natural phenomena are similar in the kind of Q index that we found for precipitation and for temperature. The left picture is for the temperature, and the right picture is for precipitation. So we have a lot of very different kind of natural phenomena that are in the same range of Q index. We have potential heights. We have extremes of precipitation, of course, that we expected. Turbulence. We have seismic emission. We have complexly developed turbulence. We have phenomena related to magnetic solar storms. We have also other kind of phenomena like global climate phenomena like ENSO. And also we have phenomena including long-term interaction like the last glacier, interglacial global climate. So I don't remember how long it, but in a very long term temperature scale. Okay. This is a very nice picture because remember we were looking for that kind of universality underlying the data, right? So this very summarize very well that kind of similarities with other kind of phenomena. Okay, so finally, just concluding, the extremes in Colombian climate are essentially non-extensive, as I showed you. temperature and precipitation extremes do not share the same universality features. But we have, with that kind of story, we have a very nice clue for describing mechanistically the extreme events. And we can use also we can use this Q index, a tool for test numerical models or even mechanical models, or just try new models. Okay, so that's all I have. Thank you.
Well, thank you very much, Isabel Cristina. Are there any questions?
Thank you for the talk. I'd like to know, when you were showing us the Q index, it was like, I have curiosity because you have like different behaviors for North Pacific zone in comparison with the middle and south zones there in the Pacific. So I'd like to know, since it has like similar vegetation densities and geographical conformations and ecosystems, why do you have like these differences here in the Q index?
In the precipitation here?
Yeah,
in,
for example,
Pacific?
You have two zones, if I understood well. You have one
Yes.
in dark gray and one in light gray.
Yes.
I'd like to know why do you have this kind of difference there? Because one could think that perhaps these weathers, I don't know, maybe similar because of the similarities in the ecosystem and biogeographical choco, perhaps. So it's like I'm curious for the difference between that zone.
Yes,
In
but
those zones, sorry.
let me come back to this, the first one here. So I don't have a complete response for that, but I know that the diversity of phenomena that are producing precipitation and also temperature is highly complex. The composition of source of variability is highly diverse. We have lots of phenomena that are working together in the same area, and there are a lot of local processes that are contributing significantly in the production of extreme behavior. So there are global phenomena. There are a very long-term spatio-temporal phenomena, but there are also local phenomena that are producing extremes. So we have a very complex structure of phenomena that are working together to produce extremes.
Okay, but isn't there like geographical similarities between both zones that perhaps you could think that they should behave similarly? I mean, yeah.
Maybe, but not necessarily. Yes, you know that Colombia, that the Interandean region is very different from the Pacific, and the moisture coming from a Pacific Ocean is located over this area, but in some parts of the Interandean region, we have also moisture coming from this area. So maybe you can infer that similar regions are similar in extremes, but not necessarily. So also the Andes are walls that are stopping the moisture that's coming from some places. So the footprint of Colombian climate is the complexity. And you don't have an entire comprehensive understanding of what is happening here.
Thank you.
So thank you very much, Isabel Castillo. Okay, so our next speaker, she is from Universidad de Antioquia, Olga López Acevedo. Can you hear us? Can you hear us, Olga? I can see that you are connected, but Olga, we cannot hear you. Olga Lucia.
Materials, so down to the scale of the electron. And these are systems that have a lot of applications in technology. They are everywhere. But it's very difficult to assess their stability. And I was interested in how we could join all the efforts that are present in the community of biophysics that study proteins and these rare events to assess these kind of questions on the nanosystems. So I'm going to show you one joint effort with Pilar Coso that was talking just before on combining metadynamics to assess the free energy of small clusters. So let's start by a bit of motivation. So nanoparticles, they exist for a long time in techniques, human techniques. In medieval times, they were obtained to make the color of stained glass. And it was known techniques, or they were obtained techniques to make nanoparticles of gold that were able to give the red color, and of silver that they were allowed to obtain very beautiful yellow. And they were a nanometer in size. But obviously these were techniques developed by through centuries. And this is now a very different situation right now. So we have a lot of nanoparticles around us in the commercial applications. Now we are talking about decades, even years. We have titanium dioxide in food coloring, even in the toothpaste. in packaging for their antimicrobial properties of silver. We have silicon dioxide in as indicating agent in food as well, and zinc oxide for food supplements. So what is the problem with these nanoparticles is that they are different from molecules in the sense that they are rather seen as a metastable state rather than this image of a molecule which would have like very deep potential energy landscape, or very much dominated by only one basin. So a nanoparticle would rather be described as the image I am showing right now, which a lot of possible isomers and competing between them, and this would be rather even a zero temperature picture. So what happens when you have a solvent, you have environment, and even when you have a temperature around playing a role? So for that, one has to address the free energy of these systems. And in particular, looking at the difference of free energy would allow you to get the probability of these two states. So one technique coming from biophysics is called the metadynamics. It works by adding a fictitious potential to the system until you reach complete separation of it. So it's kind of all the atoms become completely separated into, let's say, a huge random walk of all the atoms. So that's once you reach this system, everything that you added, when you add up everything that you added to it to separate it, then it becomes the free energy of the system at that given temperature. And this is an image that summarizes this metadynamics idea that you add another potential, and then you flip it and you get the free energy of this system. So we were wondering, can we use it now to study the free energy of a quantum system? So in principle, yes, because for materials, one very common or used approximation is the Born-Oppenheimer approximation, where we use the nucleus as point particles that they're rather described as classical particles, and the electrons are described with this cloud of probability cloud. And once you have these two separated, so every method that you use for classical systems, like metadynamics, could be directly applied if one uses the forces from the electrons that are described at the quantum mechanic level. You use it for the nucleus. So we made this combination, and this is an example of a first result where we were looking at the free energy landscape of silver-3. This is a small cluster which has 3 isomers, and we were able to obtain this very nicely, these 2 basins, A and B, of the 2 known isomers, so the triangular shape and the chain-like structure, and even the dissociation, which would be at the C side. But this was using some code that were available at the time, which was not very much flexible, and we decided to go on with this kind of positive result to do a full implementation between 2 codes that are called ACE and Plummet. So we went on, Daniel went from the undergraduate to master thesis to work directly on this topic, consisting of then an interface that would take all the machinery that is known in this biophysics community, that is in the Plummet code, and it needs to be combined with an MD engine, which in this case would be the ACE. And the reason to put ACE is that it has, in itself, it's an interface with a lot of materials, codes. You can find most of what is used, both quantum and classical, here in the list to the right. In particular, I'm participating of the community of GPO, so that's one of the reasons I wanted to get this together. So with this interface, we went on to study silver 5 cluster and silver 6 cluster. But this numbering means the number of atoms that are combined together in the aggregate. So this is a particular silver 5. It has a lot of isomers, as expected from a cluster. And we use this description inside the collective variables to be able to describe these free energy systems. Most of in silver 5, most of the free energy is really dominated by only one isomer, and let's say as seen here. So we could follow from in different temperatures, 10K, 100K, 300K, how this dominant basing was still rather the main isomer. But what we were interested in this particular point was something that worries very much the community of material science, which is what is the convergence, because our methods are so expensive that one needs a very precise, not very precise, but a good estimate of how much resources you're going to invest for a particular system, for a particular project. So we went on to doing average of the finite energy difference, free energy difference between the two basins, and doing bootstrapping to see the convergence of the free energy difference. And then we also got encouraging results that we were reaching with 5, 6 trajectories, or averaging of trajectories, the error of the methods. So that was rather encouraging. We went on to a more complicated, more interesting system. So here is an experiment showing silver isomers as a function of the size. So these are experiments where they are formed at high temperature, but they are cooled and supported. And once they are supported, one can measure their optical spectrum. So if you see the lowest silver clusters, the silver 5, silver 4, silver 5 here in top left, they have only one isomer dominating, but starting from silver 6, there are already some competing isomer, but with a very high energy. So that was the question. So how could it be that this could be appear in the optical spectrum? And there is also a secondary question, which is also in the cluster community, so explaining the transition between 2D and 3D systems. With the size, the 3D systems become the lowest in energy isomers, and the smaller size, they are rather planar. At some point, there is this 2D, 3D transition that happens. And is exactly silver 6 in 6 atoms for silver. So we went on to look at or apply our combination of free energy metadynamics estimator and the forces coming from ab initio quantum mechanics. And this is the result. So we have one basin which is dominant, but as we increase the temperature, it becomes it's competing with the other basin. And we did now as estimate of the probability, and with that estimate, we could simulate the optical spectrum and how it would look. So we have we would have a good explanation if this would be the experiment at 300K, but it's a much lower temperature, so it's not yet the end of the problem. With that, we went on to look more as a proof of concept that we could do this kind of metadynamics inside a solvent. And so we simulate the dissociation of silver 2. At the right is how you have only one basin or one minima in vacuum. And when you plug water, it seems that you start to create a secondary basin that would allow the stability of this silver. But this is still under development. for those simulation I showed you, we were talking, we were obtaining rather of the order of hundred of thousand simulations, which for DFT is, or any quantum method is really, it is really too long still. So we had to think and start to devise strategies to make this accelerated. And of course, there are a lot of very good techniques nowadays for this. And so we started to look at the use of normalizing flow, which are generative models that allow to mimic or determine any density and propose samples from this density, starting for example, a uniform density or a Gaussian density. You optimize the model to be able to transform that density into the density that you want to approach. So we use these normalized flows to start to propose these isomers, and through Monte Carlo chain start to assess the free energy. And this is an still ongoing project, but we have encouraging results that we may reduce by an order of 10 at least the number of evaluations of the quantum evaluation that we need for determining the free energy. Here, the machine learning is used rather as is really just an accelerator, because the errors and all the accuracy is still resting on the DFT approximation level, for which there is a lot of other studies that we know how accurate or how much what we can trust and when. And combined with the Monte Carlo, which is also a very well defined technique. And this is just used for acceleration, or just maybe is too simplistic, so that it will really be a key to the method. But as I have as a question, more than an answer, how can we integrate even more machine learning methods in this kind of project, or in this kind of questions? And with the group of collaborators, we have been looking at the question of interpretability in machine learning. So it's for another project where it's really focused on healthcare problems. But to my surprise, and I wanted to bring these last two slides to show you that there is really a huge amount of possible techniques to do interpretability in machine learning. So you have not only, or the most common, which are perturbation methods or gradient based. There are methods which are based on a post hoc approach, meaning that once you have the model, you will look for and extract information on how the model is working. And but that's not the only possibility. There is also another approach, which is rather called model-based, or also called as intrinsic, where the approach works by really embedding the interpretability request into the model itself. One simple way to do this kind of model-based would be to describe or use algorithms starting from the simplest one, and only go to the highest in complexity once you really are sure that it is not the appropriate level. But surprisingly, in healthcare, there are literature showing that even with some really logistic regression, you would have performed as well as very fancy neural networks. So I have here just like model showing this model base. There are theoretical results showing that this kind of optimization, imposing more strict conditions on the model can be successful. And I have here a few examples. For example, RiskSlim will do this kind of strategy, or Protopinet, also known as This Looks Like That, for images, are following this kind of ideas. And then with that, I would like to finish and thank you all for, and Daniel Sucerque, Cristian Parra, Pilar Cosio, and Ana Molina from the university. Now Pilar moved to the Flatiron Institute, and Marilu Gabriel is also working in this project. So I would like to thank you, them and you for your attention.
So thank you very much. Are there any questions, comments? Okay.
Thank you, Garcia, for the nice talk. My question is the following. One of the ways people have found in the last 10 years to measure differences on free energy is to use Jarzynski theorem or Crookes relation by setting a non-equilibrium protocol. No? So by going very fast to force one of the configurations and then going back, yes, allowing the previous one. No, is that possible to use that? Do you think is that possible to use this method for the silver structures you have?
In classical setting, probably not, because you have a very well-defined relation between the systems. Okay, depending on what, or you really are in out of non-physical or non-chemical setting. But here, the advantage of the quantum is that you can force the system to go to very to any structure, actually, because the Schrodinger equation is solved in every step. So I would say yes, that would be another strategy.
Thank you very much.
So I do have one question, Olga. Did you mention that with using these methods, you achieve 1 order of magnitude faster, so 10 times faster?
It looks like yes, but it's not fully conclusive. But we first started because of the efficiency, but there is also another reason to go on to using this kind of machine learning based approaches, which is that you don't need to use collective variables or any other approximation, and then you avoid a lot of the problems associated with this kind of projection or simplification of the system. So both, even if you get the same efficiency, it still would be a winning method over just metadynamics.
Okay. Any other question? No? So thank you very much again, Olga. And our next and last speaker of the day is Diego León Luis González from Universidad del Valle. Diego, are you
Hi, can you hear me?
Yes, we do. Mm-hmm.
Okay. Let me share my presentation. Okay. Can you see my presentation?
Yeah. Yes, we can. Mm-hmm.
Okay. First of all, thank you, Gabriel, for the invitation. I'm going to talk about the steady state of a two-species annihilation process with separated reactants. This work was done in collaboration with Professor Gabriel Telles and with the collaboration of Cecily Vargas, which is a former undergraduate student of the Universidad del Valle. Okay. Well, as you know, reaction diffusion systems are used as models for the description of many different phenomena, such as pattern formation, growth by aggregation, evolution, of reactants by chemical reactions, disease spread, etc. Well, the basic mechanism for matter transport in this system is diffusion. And once the particles reach the interaction range, they interact. And if the typical diffusion time is much more longer than the typical reaction time, we say that the system is diffusion limited. In this case, the local fluctuations in the density are quite important. In the opposite case, the system is reaction limited. In this case, the components of the system are usually mixed. And of course, in general, reaction diffusion systems are difficult to study because we have nonlinear evolution, we have nonlinear processes, which are also out of equilibrium. So we want to study one of those systems. Well, this system was proposed by Oyuelos in the 90s and consists in a one-dimensional lattice with two end sides and two types of particles, particles A and particles B. The reaction between these particles is given by this expression. We have an annihilation reaction. Just one particle per side is allowed. Here, beta is the reaction rate, lambda is the hopping rate, and we have the position of particles in these sides of the lattice. Well, at t equals 0, all lattice sides are occupied, but the A particles are at the left of the system and the B particles are at the right. In the steady state, we have a balance between reactions and the position of particles. We want to describe the steady state of this system. Well, what quantities can be used in order to describe the statistical behavior of the system? Well, the first one is the joint probability to find the rightmost A particle at position XA and the left MB particle at position XB. The second one is the gap length distribution. L is the distance between the RMA and the LMB particle. And the distribution of the reaction positions. And of course, we can also use the density profile, which is given by this average. Well, we write an exact master equation for the evolution of this distribution, but it is impossible to solve this equation because it is written in terms of the probability of configurations which cannot be expressed in terms of the joint probability. However, from this equation, it is possible to find the master equation for the evolution of the gap length distribution using this expression. And we find this equation for the evolution of P. This is describes the behavior of the gap length distribution in the steady state. These are the boundary conditions. Here, J is the particle current and K is related with the reaction rate. The solution of this equation is given by this expression. As you can see, the behavior of the distribution depends on the ratio between the time scales of the system. J is related to the deposition rate, D is related to the hopping rate, and K is related to the reaction rate. In this limit, the system is in the diffusion limited regime, and this equation reduces to this expression. As you can see, the probability to find the RMA and the LMB particles close to each other is quite small for small values of L, which means that we have an effective repulsion force between those particles. For large values of L, we have a Gaussian behavior. On the other hand, in this limit, the system is reaction limited, and we have a completely different behavior. As you can see, we don't have an effective repulsion force in this case, and the distribution behaves as an exponential function. So in order to find an expression for the joint probability, we use this change of variables. L is the gap length between the particles, and kappa is essentially the position of the center of mass. Well, we assume that these variables are uncorrelated, so an approximation for this distribution is given by a product. This is the gap length distribution, and we assume that the evolution of the center of mass of the particle follows a Gaussian distribution, which means that the center of mass evolves by diffusion. Well, we can recover, or it is possible to pass from this distribution to our original variables, and we find this expression for the position of the particles at the reaction front, these ones. Okay? Well, from this joint distribution, it is possible to calculate the marginal distribution for each particle, and these are our results. In this figure, dots corresponds to the numerical results from a kinetic Monte Carlo simulation, and lines corresponds to the analytical model. As you can see, the marginal distribution of the particles are quite overlapped for this value of beta. Here we are in the reaction limited regime. At the right panel, we have some typical configurations of the system. And as you can see, these particles are confined in a small region close to the center of the system. In contrast, in the diffusion limited regime, these particles have more space to diffuse, and that's why we have this kind of distribution in the case when the system is diffusion limited. Okay, well, now these are our results for the gap length distribution. Again, dots correspond to the numerical results and lines to the analytical model. As you can see, the agreement between analytical and numerical results is very good. And as I mentioned before, in the case of the reaction limited regime, there is no repulsion force between the particles. So it is very likely to find these particles close to each other, and the distribution decays exponentially, as you can see here in the inset. In the case of the diffusion limited regime, the behavior is completely different. Here we can see that we have an effective repulsion force between the particles because of the reaction, and we have a Gaussian behavior for large values of L. And this plot shows our results for the distribution of the reaction sites. As I mentioned before, we assume a Gaussian distribution for this stochastic variable, and our numerical results shows that this is a reasonable assumption. And this behavior works very good for both regimes, for the reaction diffusion regime and the diffusion limited regime. The only difference is that, of course, in this case, in the diffusion limited regime, these particles have more space to diffuse, and because of that, this distribution is wider, okay? Well, the next step was calculate the density profile. In the steady state, the density profile satisfies this equation. Here, F is the reaction kernel. In the case of the DL regime, we propose that F is proportional to the distribution of reaction sites, which are proportional to the product of the densities of particles. However, for the reaction limited regime, the kernel is quite different. Here, in the diffusion limited regime, the reaction kernel is the same for both type of particles. But in the reaction limited regime, this F depends only on the marginal distribution and it's not the same for both kind of particles. Here we have our results for the density profile. And these lines, the upper lines corresponds to the diffusion reaction limited regime, and the lower lines to the diffusion limited regime. As you can see, the behavior of the density profile is quite different for both cases. And in particular, the density current J is the slope of the density profile. So as we can see here, in the DL regime, the particle current is constant in this region, and then decreases, monotonically decreases to 0. But the behavior of the particle current is quite different for the reaction limited regime, because in this region where we have reactions, we have the particle current increases. Okay, so the behavior is completely different for both cases. Here we have our results for the gap length distribution and the density profile for several values of beta. And this plot shows that the gap length distribution is more sensitive to this parameter than the density profile, because, for instance, if we focus in the blue lines for these values of beta, as you can see, the density profile is quite similar for those values, but the gap length distribution is completely different for these values of beta. This is an important result because most of the experimental results focus on the calculation of the density profile, but our results suggest that it is more convenient to measure the gap length distribution because it's easier to extract microscopical information of the system using this distribution, that distribution. Okay. Finally, wow, what happened here? Some conclusions. First of all, the joint probability distribution, the probability to find the rightmost A particle at position XA and the leftmost B particle at position XB. This distribution contains fundamental information to describe the statistical behavior of the system in the steady state. Well, the reaction is localized in a small region close to the central part of the lattice, but the reaction affects the density profile of the entire system, which suggests the presence of the strong correlation between the particle position. Well, next, the distribution of the reaction position follows a Gaussian form for both regimes. So this shows that the position of the center of mass of the particles evolves by diffusion. Well, the reaction limit regime, the particles are more mixed than in the diffusion limited regime. The reaction kernel is quite different for both regimes. In the first case, F is proportional to the product of the densities, and in the second case, the reaction kernel depends on the marginal distribution. This means that the reaction mechanism for both regimes is different. And finally, work in process, we are using our model to analyze experimental results. Here we have a couple of plots from an experimental setup done by the group of the Professor Teitelbaum. We took different calcium compounds. And here in the left figure, we have the behavior of the position of the center of the reaction front. And we have a very interesting behavior because, as you can see, it's not completely diffusive. And these are the results for the width of the reaction front. So we are now using our analytical and our numerical and using numerical simulations in order to reproduce and describe these experimental results. And that's it. Thank you so much.
So thank you very much, Diego, for the nice talk. Any questions?
Thank you, Professor Diego, for your talk. My question is, this is for one-dimensional chain, right?
Yes, it's a one-dimensional system.
Yeah, but the boundary, at the boundaries, they are free or have some boundary?
No. At the boundaries, we have the position of particles because in order to reach a steady state, we need a balance between reaction and the positions. So in these lattice sites, we have the position of particles.
Okay, so it's not possible to use periodic boundary condition, right?
Yes, it is possible, but in that case, we have two different reaction fronts, one here and the other one in this region.
Okay, okay, thank you.
Last question. No? Okay, so let's thank Diego again. Okay, since this was the last talk of the day and of the workshop, and since I'm the one standing here, so I have to say a few words to Jose Daniel and Gabriel. I'm really happy. I'm really I'm happy that you have done this again for the fourth time. It's now a tradition, so I think you should keep doing it. I know it's not the point. I mean, at this point you're kind of exhausted, but I really want to thank you in the name of all that assistants here and all the community that you have been building during the last years. Now we have a lot of students. Some of them are still coming here now as in other situations. Some of them are abroad. But I really think the event has had its impact in Colombian science. Yeah, personally, I think it's one of the best ones. I'm looking now again forward to it. So thank you very much. I have a present for you. It's in this is a small present, yeah. So thank you. Yeah.
Well, no, thank you very much. This is really unexpected, but thank you for, thank you for the gift. And well, I want to thank again for the speakers, John, Gonzalo, and Hans. Have come here and share your knowledge with us. It's very important here to have this kind of tutorial courses to get actualized in the latest advances in statistical mechanics. And well, of course, we have to thank our sponsors, both the universities, the Faculty of Science of Universidad Nacional and one from Universidad de los Andes and the physics departments of Nacional and Los Andes, which gives the financial support to do this. And thank you all for coming, whether it's here or online. And maybe I give.
So really, thanks to all. No, thank you especially to the speakers, and to the course speakers. No? Thank you, Gonzalo. Thank you, John. Thank you, Hans. Thank you for coming. Thank you. This will not be possible without the participation and the effort of all invited speakers and all oral contributions and poster contributions. Thank you very much. I want also to thank the Department of Foreign Affairs of the National University who support us, to the Physics Department, and also to all the administrative staff, yes, in all different divisions of the Faculty of Sciences. Yeah, this is like a dream that done reality, you know, after 6 years of pause because of the pandemic. Now we are taking rhythm again. So it's good to know, to see how the area of statistical physics is evolving in Colombia, no? How the topics are more diverse and they are and the works are really good. No, thank you for sharing these works with us. And yes, so we will try to maintain the tradition. Also, if you want to help us, you are kindly invited. So really, really, we are very happy and very glad to have you here. No, thank you for the effort. No, this is 6 p.m. Friday, and you prefer to be here. This is very significant for us. So thank you.
Well, so I will see you here in 3 years, in 2026, next one.
I forgot the sponsor of the central so from the division of research and extension in Bogota, who also support us, and the